Okay, today we want to talk about the basic cryptography concepts in security and computing. This is an introduction of the basic cryptography and talking about the history of the cryptography and also some algorithm in basic cryptography. Please join us about this lecture. So, cryptology is a science of secure communication and is formed from the two Greek words, cryptos and logos. Cryptos for hidden and also logos for word. So it is underlying technology used in most modern communication to preserve confidentiality and integrity as well as to apply authentication. Application here using the cryptography include the passport systems, ATM, and also e-commerce. It is a science that includes studies from other disciplines such as mathematics, computer science, electrical engineering, as well as linguistics. And it is generally made of two separate parts, cryptography and cryptanalysis. Cryptography is about the making and using secret codes, and cryptanalysis is talking about the breaking secret codes. And it is important to have both these parts because they serve as check and balance against each other. So if the codes can be easily broken, so then they need to be redesigned and reconsidered. Historically, cryptology has been used solely for confidentiality and for example, to preserve secrecy of a text. This only involved concepts related to encryption, conversion of the meaningful text into something incomprehensible, and vice versa. Some example here, and using the Skytail by Spartans and Caesar Cipher during the Roman age. And also the modern era has initially continued on this trend, but include more complex method and calculation for both cryptography and cryptanalysis. And also mentioned that encryption was vital during the World War I and World War II. Also, cryptanalysis was equally important in understanding what the enemy was planning. So cryptology here evolved to its current form today, where it is used for multiple purposes, including authentication and integrity checking. So as you can see here, after World War I and II, we are going to the age of the modern cryptography with using the DS symmetric encryption and also RSA public key encryption invented in 1977. And then we are going to talk about most of them in this course. Let's talk about the terminology in the cryptography. So the first things is the plain text and ciphertext. Plain text is the original information or original message we want to encrypt, and ciphertext is unintelligible gibberish or coded message or ciphered message, or after encrypting a message we have the ciphertext. And also cipher is called an algorithm for transforming plain text to the ciphertext and also vice versa. And then we have the term key. Key is a secret parameter used by cipher and only known by receiver and sender. So it means that communication parties just knows these keys in the symmetric encryption. And then encrypt or encipher and decrypt and decipher. Encrypt means the process of transmitting or transforming the plain text to the ciphertext, and decrypting or deciphering is the process of reverse process of the encrypting. It means that transforming from the ciphertext to plain text. So these terminology are connected during these diagram you can see here. So we have a plain text, for example, here we have the plain text. We call it, we attack at down, and then you can see here, when you use the keys, secret keys here, this is the encryption process. So we use the keys and encipher algorithm to encrypt the plain text to the ciphertext. So this is the ciphertext. And at the receiver, we need to decrypt this message, because in the receiver, we receive this message as a ciphertext, and we need to use the same keys here to decipher and use the decipher algorithm to provide the plain text and read it. Okay, so these all terminology are shown in this diagram. Okay, modern cryptography, as a father of the modern cryptography, is Claude E. Shannon. Claude E. Shannon an information theory in 1949 and writing papers about the communication theory of the secrecy systems and the mathematical theory of the communication. So it could be assumed as a starting point of the modern cryptography. So then there was a pause as governments, NSA or GCHQ, tried to protect their interests, classifying research and hiding results until mid of the 1970s. In 1970s, two major events in crypto as a DES in 1975 and Diffie-Hellman in 1976 we have. So DES succeed by AES in 2001, and current standard we use here is 256-bit AES. 256 means the size of the key in AES. So public key cryptography, popularly known to be invented or developed by the work of the Diffie-Hellman in 1976 for the key exchange, and also RSA in the 1979. Also popular that El Gamal in 1984. So however, El Gamal suffers from the ciphertext expansion. So here in at the GCHQ, Elise, Cox, and Williamson claims that to have come up with the first PKC in 1973, but a scheme was classified by British government. In PKC means public key cryptography. So let's go and talk more about this. For the cryptography, you have to know about one of the most important principles in cryptology, that is called Kerckhoffs principle. Kerckhoffs principle tell us a crypto system should be secure even if everything about the system except the key is public knowledge. It means that maybe everyone knows the algorithm of the cryptography, but if they didn't have the secret key, they cannot decrypt the message. So the crypto system's security must be rely on the secret key, not the algorithm. Okay, let's talk about the classical cipher here. So we are talking about the classical cipher, and at the first, we are talking about the traditional cipher. So in the earliest and simplest form of the cipher, we use the character and was the unit of data to be encrypted. So these characters, we use it as a substitution technique use or transposition technique use. So it's used in the traditional cipher. For example, let's talk about the keyless transposition cipher. So for example, the first one we call rail fence cipher. So in this case, we use some message and we want to do it in the encrypt this message. So in rail fence cipher, we use, for example, in 2 rows, 3 rows, or n rows. These rows we can assume that as a secret key. So as you can see here, we write it in 2 rows, but like this: meet me at the park. You can see the message is meet me at the park. So the first character at the first row, second character second row, then first character, third character first row, fourth character second row, and so on. At the end, you can read it by rows. So we have it as an MEMATEAK You can see this is the ciphertext. So we call it a rail fence cipher. Okay, and also if we want to encrypt this message, we must use the same rows as a encrypted message. So for example, for this is my home, if you use here, you can to encrypt it like this. So we have to use rows 2. This is my home, and read it by this TIIMHMHSSYOE. And also for the 3, you can see here the encrypted message or ciphertext. So also for rows 3, you can use it like this. So you write Polly wants a cracker. So Polly wants a cracker. And then we read it PYTRE and so on. Read rows by rows. We use it for the encryption of the rail cipher. As I told you in a slide before, when we want to decrypt the message, we have to use the same rows and put this message, as you can see, this, for example, this message like this, T, E, A, G, and other character based on this one, and then read it like when we put it in the message. So as you can see here, we have to read it like this, 10 Traba 1, okay, 10 Traba 1. This is maybe Malaysian message or something. So as you can see here, we can read it like when we put in the cipher plain text in the rail cipher algorithm. Okay, now you please try to do the encrypt the following message and also decrypt the following message using rows 2 and rows 3 for both of them. Okay, now we are going to talk about the substitution cipher. So substitution cipher method used to substitute one symbol with another one. So if the symbol in the plain text are alphabetic character, replace one character with another. And also, for example, replacing character A with D or T with Z. And if the symbols are digits 0 to 9, we can replace 3 with 7 and 2 with 6. We use it categorized as a this kind of the method because we categorize it as a monoalphabetical, and then we have also polyalphabetical method. So as you can see here, in monoalphabetical substitution, if we cipher or encrypt the A in plain text to the D, every A in the text is changed to the D. But in polyalphabetical, maybe at the first time A is going for D and the second time A is going for example, Z. So it could possible to convert any of the A or any of the characters to another one based on the any assumption or initial assumption about that. So in monoalphabetic substitution, we use also between the characters between the ciphertext and plain text are 1 to 1. So let's talk about the Caesar Cipher as a very simple part of the encryption. We use this method. In Caesar Cipher, we use some method for shifting the message in the alphabetical form. What it means, please see that. So if you can see here, C or ciphertext is the encryption of the plain text. How we can do it? For example, we use some number here. So as you can see here, P plain text is added to the tree, and mode of 26 because we have 26 character in English alphabet. And then for decryption, we use the subtraction here to use the same number, 3 addition here, subtraction here. So as you can see here, for example, we have A, B, C, D, E, F to Z, and we have 0 to 25. When we use the method, for example, we use the 3, so A is 0 plus 3, we have 3. The character with the 3 is D, so A is changed to the D. For example, another character, we have P. When we want to encrypt the P is 15 plus 13, we have 18. So the cipher character is S, or encrypted character is S. Okay, let's see another example of here. You can see here the plain text. Everywhere we have the alphabetic, we use a key here, for example 3. So we shift these plain text or shift these alphabet like this, but shift is circular. What it means, after Z we push these A, B, C at the end. So we have, for example, with key 3, A is going to D, B is going to E, and so on, and Z is going to C, Y is going to B, and as you can see here. And also, if we have a plain text, okay, an encryption using the 3, as you can see here, for example, character M, meet me after something, okay, M is 12, as you can see in the in alphabetical order. So we use M as a 12 plus 3, so we have 15. 15 is the P, so meet is going to, M is going to P. For others also, you can see, we can find it in the, and also you see that this is the monoalphabetical method. So we have 2E, both of them going to H. If we have another M, you can see here, M also going to P for both sides. So this method is the monoalphabetical method. So generally, when we use the general shift cipher, this is the same method we use here. So plain text from Alice, in cryptography scheme, we use Alice and Bobs for the sender and receiver. So Alice here using the plain text, and this encryption algorithm with the keys to make the ciphertext and send it to the Bob as a receiver, and Bob use this ciphertext and this algorithm with the same keys to decrypt the message and have the plaintext again and read it. So here, as you can see, the general shift cipher using addition and subtraction to the key here, and it's very simple to use it. Okay, let's talk about the, in this case we want to talk first about the reading the clock, and then using in cryptography. So it could help us to make it very simple than before. So as you can see here, the clockwise method is going to from the up, as you can see, from here, and then write this. So we use what's 2 hours from 4 p.m. It means that what's 2 hours from 4 p.m. is here, and 2 hours after it is, we call it 6. Also 10 hours from 4 p.m. we have 4 p.m. here. 10 hours, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is again 2 a.m. and then so on for that. So you can see here we can use the clockwise and clockwise method for encryptions. So let's see it in the next slide. So you can see here, for example, we have a method and we want to encrypt the cat. So we can use these circles and put all the alphabets like this here and use it for the encryption. So as you can see, it is totally circular and we can use it simply for our work. So how it works, for example, we want to encrypt the cat with the key 7. So C is going to here, okay? So we want to know that what is the encrypted by key 7. It's enough to add something 7 to C. So C, D, E, F, G, H, I, and J. So after 7 we have 9, we call it J. Also for A, we use from A. So this is the A as a 0, 1, 2, 3, 4, 5, 6, 7. So we have H for the A, and for T, you can see T is here. 1, 2, 3, 4, 5, 6, 7, and T is going to A. So cat is encrypted to JHA. Also for dark, we use with key 16. It's enough. D is 3 plus 16, we call it 19, and the 19 one is T. The next one, O, is 14 plus 16, we have it 30. 30 mod 26 is 4, and 4 is here 0, 1, 2, 3, 4, E. And then 6 plus 16, we call it 22 mod 26, it's going to 22, and it's W. So the ciphertext could be TEW. Also for decryption, we can use the same method, but we use the subtraction here. So these kind of the circular thing like clock would help us to do it faster and in a better method and better way to do it. Okay, so you can use it yourself and check it what's happening in decryption and encryption. But now for an example, I told about this one. So CHEUD is a ciphertext with the key 3. So C is the 2 minus 3, we call it minus 1, mod 26, we call it 25, and this is Z. And then H is 7 minus 3, we call 4, 4 is E, ZE. And then E is 4 minus 3, 1 is B, ZEP. U is 20 minus 3, 17 is R, and D, 3 minus 3 is 0, A. So the message plain text is zebra, and the encryption text was CHEUD. Okay, now you can try and work on that using car, top, and FYW and TJT with the keys announced here. So car with K5, top with K14, and 4 and 9 for the decryption. Another method for the substitution cipher used that in the last time we used the additional subtraction. Here we must use the multiplicative cipher. So in multiplicative cipher, you can see here we multiply the key onto the message and we use the K-1 under C. So what it means that you can see here in the multiplication. So as you can see here, for example, the plain text is hello. So H is 07. Encryption 0 and key is the 7. So encryption between 07 and 7 multiplied together is 49. 49 mod 26 is 23, and the result is X. Then E is 4. 4 multiplied 7 is 28, and ciphertext is C. And other for we have the XCZZU here. So the ciphertext would be XCZZU. As you can see here, also in affine cipher, we can define the affine cipher and using two keys, K1 and K2. So in K1, as you can see here, we use K1 multiplied to P plus K2 mod N. So what it means that you can use two keys and the plain text to make the ciphertext, and also at the end in decryption method also use the same K1 and K2 and use KY-1 here to provide the plain text again in the receiver. So as you can see here, we have to use in the affine cipher and the bit key pair Y7 and 2 and use ZEBBW here and get the hello message here. So here the decryption is 25 minus the first key 2 and multiply 7 minus 1, 7 power of minus 1, and we have the P7, it is H. Again 4, we have E. Again 1 and 1, we have 1 and 1, I and I, and L and L, and for W is 22, we got O. So the result is hell. Just mention that if we use K1 as a 1, so it is the simple additive cipher we use at the, for example, Caesar method or any other method. So this is the affine cipher example, you can use it. As a Kerckhoffs principle, we talk about this. The key size is very important. So if because the encryption security is based on the keys. So if the key size is too much, so it's more secure than the key size is very simple. For example, the key size in additive cipher, multiplicative cipher, and affine cipher is 26, 12, and 312. So as you can see here, these methods can be broken very simply because we can use all the, we call it the exhausted attack, and also we call it the brute force attack. So they can use and check all the key, possible key, and find the plain text. So as you can see, the key size is very, very low, so we can decipher the message very simply. How? You can see at the second slide. You can see we are going to cryptanalysis of the Cipher cipher. So we have only 26 possible cipher. For example, A is going to A is going to B, A is going to C, and so on. So we have used the brute force check for all of them. Let's see an example for this. So as you can see here, the cryptanalysis of Cipher cipher we can use here. So we have the cipher text like this, and we can do like check all the possible key. We only have 20 key from 1 to 7. You can check here. So key is 1 is not a good message, 2 is not a readable message, 3 not, 4 not, 5 not, 6 not, and 7 yes, not very secure, the plain text. So as you can see, doing the decryption using all the possible key, we can get the message here after 7 try just. Okay, so it's very simple to decipher, and cryptanalysis, even we don't this method as a substitution method, even we didn't have the secret key. So now it's your turn to do it for this message and try to guess what does this ciphertext means. So as you can see here, for monoalphabetic cipher, rather than just shifting the alphabet, we can use also shuffle or jumble the letters arbitrarily. So it could help us to do it more secure for our message. So each plain text letter maps to the different random ciphertext letters. Hence the key is 26 letters long. So as you can see here, A, B, C, D, E, F, G, for example, the plain text is going to D, K, V, F, Q, F, and it's totally also shuffle as a changing the characters also. So as you can see here, for example, in encryption, we used A, B, C, D, E to going to K, C, P, S, V, M, and so on. And in the decryption process, we can use the reverse function and change K to A, C to B, P to C, and so on. So Friday is going to be MJDSKZ, and MJDSKZ could be after, for example, M is going to F, J is going to, let me check, R, D is going to I, and S is going to, as you can see here, D, and K is going to A, and Z is going to be Y. So the result is Friday. So the question here is what about the keys here? So we have the 26 factorial keys, or 4 multiplied 10 power of 26 keys. It's very, very, for example, big enough for the checking in brute force attack. But is it safe? So we can assume that is it safe? So the answer is no, because of the problem in here is the language characteristic, and what it means you can check in the next slide. So as you can see here, frequency of the occurrence of the character is very different in English languages. For example, using the English most frequently used character are E, T, R, N, I, O, A, S, and less one and very rare one is Z, J, K, Q, X. And you have some other characteristic of here we can use in the decryption. How is possible? Please check in the next slide. So as you can see here, we know the probability of the occurrence or frequency of the letter, English letter, are like this. So we have the percentage of occurrence of A to Z. So we know that, for example, the most frequent letter is E with 12 point something percentage of the occurrence. And the next one is T with 9%, 9 point something occurrence, and so on. So we can use this characteristic for cryptanalysis of a message. Okay, let's talk more about that. So we have the percentage of the occurrence, English character, E is 12 something, T is 9 something, and so on. And also we have the frequency of the diagrams and trigrams here. So TH, HE, IN, ER, and so on, and THE, ING, and HER, ERE, and so on. So we have all these frequencies based on the occurrence. So we can use it for cryptanalysis of our message as we saw in the next slide. So let's go and start to cryptanalysis this ciphertext. We have an example of this ciphertext. You can see it's very weird and we cannot read anything here. So we can count each of the characters and see the relatives in the occurrence table in the latest slide. So for example, after counting this, we can guess P and Z are E and T because their occurrence in this cipher message are too much. And then ZW as a TH and ZWP as the THE. So after doing that, we can simply cryptanalysis the message. And the message plaintext is this one. It was disclosed yesterday that several informal but direct contacts have been made with political representative of the Vietcong in Moscow. So as you can see here, we simply, as the key space is too long and too much, what we can cryptanalysis this message based on the language characteristic. So in polyalphabetic substitution, for example, in any message, A at the beginning could change to D, but at the end of the message, it could change to N. So A is not going to be one-to-one to the cipher, or any character is not one-to-one, and it could be one-to-many, as you can see here. So here, they make the cryptanalysis harder with more alphabet to guess and flatter frequency distribution. So for example of this message, we can call Vigenère Cipher. As you can see here, for each of the characters, we use any keys, and the cipher is totally different. As you can see, T is going to O at the first, but T is going to T at the end. So it means that it's not same during the message. Okay, another one we can use is product cipher. So cipher using substitution or transposition are not secure because we check that with the language characteristic and simply broken them. So we can use the several cipher succession to make harder, but two substitution make a more complex, for example, or two transposition make more complex transposition. But a substitution followed by a transposition make a new, much harder cipher. This is bridge from the classical to modern cipher, and also we use some other mathematical method in the new modern ciphers. The another thing is used is Rotor machines in the World War II. So Germans use Enigma, and Allied use the Hagelin, and Japanese use the Purple method. So they use some Rotor machines to do it. For example, with the 3 cylinders, they have 26 power of 3 or 17,576 alphabets. So So they use in the World War II the message like this, haggling an Enigma Rotor machine, and they use for encryption and decryption. So as you want to know more understanding about that, these methods are broken during the World War, and you can see a very interesting movies about this. I try to tell you, please see this movie that is called The Imitation Game, about broken the Enigma in the World War II. Please see these movies. And then thank you very much for seeing this video, and please ask me in the comment if you have any questions. Okay, thank you very much for watching my video, and please support us with subscribe, like, and also comment, and also introducing this video to your friends. Thank you very much.